Okay, so let's give you a quick review for previous class. In previous class, actually, we introduced there are two there are two defects, included the Schottky defect and Frankel defect form in the ionic solid. And the Schottky defect means that a pair of cation vacancy and anion vacancies was formed in the ionic materials. And a pair of, that means the number of anion vacancy will be the same with the numbers of cation vacancy. And Frankel defect means that in this case is the cation silver jump or diffuse to interstitial site and left a vacancy here. So this kind of defect, we call it is a Frankel defect. And regarding to the silver, actually, silver is obey the interstitial C diffusion mechanism. And then we show you how to obtain or estimate the self-diffusivity of potassium ion or chloride ions materials with Schottky defects. So as long as you know the vacancy fractions times the vacancy diffusivity for the vacancy and times the correlation factor, then you can get the self-diffusivity for cation and anion. So based on this concept, and also you know the Schottky defect means the formation of pairs of vacancy. So the number for the VK will be the same with VCL. So this equation is it means that there's a Schottky defect form in your material. So will be K equivalent can write down as an exponential Schottky defect formation energy divided by KT. And this will be equals to this. So you can get the Vk equals to Vcl equals to exponential minus Schottky defect formation energy divided by 2kT. And based on this results, you can formulate the diffusivity for potassium ion. Is a G means the because this is ion materials and all the and the diffusion probably will involve different mechanisms. So we'll put a G here, and will be the XVK dk potassium jump into the vacancy at potassium site to diffuse. So, and correlation factor. And the same thing, you can obtain the self-diffusivity for of chloride is a G XVCl diffusivity of chloride big guy diffuse or jump into vacancy at chloride site in terms of correlation factor F. Based on this, you can simply formulate the vacancy fraction at potassium site is the Schottky defect formation energy and separate them in the entropy term and entropy term. And the diffusivity part will be involved like a migration energy. Here is a cation potassium jump in vacancy at potassium site. And the same idea can be applied here. So the vacancy fraction of chloride at chloride size, this one is equal to this one. So separate into the entropy and enthalpy term. And also the migration energy will be involved in an ion chloride migrated into the vacancy at chloride site. Okay, so now you can, in this potassium chloride FCC structure ionic materials with the Schottky defect, we can easily get the self-diffusivity of potassium ion or chloride ions. And next, we are going to dope some dopants in these ionic materials. And next, and here just remind you, the self-diffusivity can express like the temperature independent term times the temperature dependent term. So as long as you measure the self-diffusivity of potassium at different temperature, then you plug the log D over 1 over T, then the slope After fitting the slope, you can get that, and so you can know the diffusion activation energy of your materials. And this energy included the Schottky defect formation energy and migration energy term. Okay, so here is we are going to show you how about if we added or dope some dopant in this potassium chloride FCC ionic material with Schottky defect. Then what's the divisibility of potassium as a function of the concentration of the dopant? So based on the results here, you know that the decay is proportional to the vacancy fraction at potassium side. So as long as we can manipulate or change this vacancy fraction at potassium side, then we can easily change the decay. Okay, some people probably will ask, Professor, how about F? As long as you choose your interesting material with a specific crystal structure, then F already be a constant. And dV is involved the energy barrier of the migration. So the migration energy usually is involved two things, right? The first is the lattice distortion. The degree of lattice distortion will proportion to the energy barrier. And the second thing is the atoms at what kind of energy state, because that will change the energy barrier as well. Okay, so in this case, in our experiments, usually the easier way is added some dopant into our material and try to manipulate or change the vacancy at the potassium side. So in this case, is we dope the calcium chloride in potassium chloride, and the calcium with 2 positive charge. And because now at a certain temperature in the potassium chloride ionic materials, there are many pairs of VK and VCl, right? And when I try to add some dopant into this potassium chloride ionic material, the calcium is going to occupy at the vacancy at potassium side, and this is 2 positive charge, and this vacancy is with 1 negative charge. So you will 2 minus 1, you become 1 positive charge here, and the chloride will at chloride side. So you have 2 chloride, so you will get 2 chloride at 2 chloride side. And because you have 2 chloride, and also you should have 2 vacancy, right? So you are going, and only 1 calcium can occupy this potassium vacancy at potassium side. So you are left a one VK vacancy at potassium side in these ionic materials. So the idea to reach the charge neutrality, all the positive charge guys will be equals to all the negative charge component. So you got this relationship between the calcium at potassium side and the vacancy at chloride side and vacancy at potassium side. And based on the semiconductor industry or fundamental knowledge you learn, even after dopant, the carrier, the positive carrier and negative charge carrier, the electrons and hole, the concentration of P and N times P times N will be equals to Ni squared. Ni is before dope, the major carrier, the concentration of major carrier square, right? So here we use the same concept. We use the negative, is a negative charge and positive charge, and equals to before, the VK prime is before dopant. So this turn vacancy at the chloride side with 1 positive charge will substitute by VK minus this term. So we use this one. So based on this equation, we can simply get the vacancy fraction at potassium side expressed like this. And based on this result, we can easily separate into 2 cases, right? the first one is the before dop, the intrinsic vacancy vacancy fraction at potassium side is much larger than this one. So you can drop this term out and you just take a square root on this one and times this. Then you will become, you drop this term out and you got the VK prime pure before dop. So this some people call it intrinsic property because the vacancy fraction at the potassium side equals to the vacancy fraction at the potassium side before dop, which only the formation here is due to the Schottky defect. Okay, but the other case would be this one is much smaller. Okay, so as long as you got this one, you can substitute this one, then you can get the diffusivity of potassium under the intrinsic material property can be expressed like Schottky defect formation energy times the dV times F. But the other case, some people call it is extrinsic cases, would be the VK prime pure before dop. The vacancy at potassium side is much smaller than the concentration or fraction of the dopant. So this one is quite large. So this term is very small. So you got the 1 plus 1 is 2. So drop the 2. So the vacancy fraction at potassium side is equal to the atomic fraction of the dopant. And you can get the diffusivity becomes to the concentration. This will becomes a constant because you know how much dopant you dope in this ionic material, right? And the dV is the same, and write down the correlation factor F. So now we know we try to draw this two cases. How we want to draw these two cases into one figure as the log dk versus 1 over t. And 1 over t and take a log on it, so you know for intrinsic material property, the slope included two terms. Well, the first one is the Schottky defect formation enthalpy term and plus the Schottky migration enthalpy term. So it will be like this. This slope will be higher, larger than this one, because this one the only term is a migration energy term, so it can be fitted in intrinsic. And the dopant part, extrinsic part will be like this. The slope of this one will be higher than this one because for intrinsic, the slope still need to consider the Schottky defect formation energy. And for the extrinsic one, actually the slope is only dominated or controlled by the migration energy term. So as long as, what's the black curve means? Actually, black curve is the experimental observation in this extrinsic ionic solid. That means if you have a doped ionic material, then you try to measure the decay at different temperature, then you can get this black curve. Then based on this the morphology and how this curve looks like, you can guess if it is the data is looks like this, you can easily fit this with two straight line. And the straight line at high temperature regime, we know it is intrinsic property. At the low temperature regime is extrinsic, the dopant dominate. But don't forget, this value, the black curve, actually is the sum of intrinsic and extrinsic effects. And also at this regime, yes, it is dopant dominate, but also the data is a sum of the extrinsic and also intrinsic effect. Even the intrinsic is quite small, effect is quite small, but still contributes little, tiny on the decay, diffusivity of potassium or diffusivity of the potassium ion. Okay, so as long as you get this fitting, then you know the HVM, right? Then you got this slope, so you can know the Schottky defect formation energy of your materials. Okay, so this is the story. And next is, we call it is a non-storage geometry ionic materials. So the example here is iron oxide. This is an ionic material. Then we dope with titanium oxide. Based on this, you know the iron with 2 positive charge and the titanium with 4 positive charge. And now we have the doped iron oxide. So if I want to try to I can directly measure the diffusivity of ions at different temperature and plot and link it as this black curve. Then you can find actually this curve's width. You can feed it with probably 3 straight line, and based on what we learned in previous slide, we know at the higher temperature region is the intrinsic property, which is a Schottky defect, dominate the vacancy fraction at iron side, and at the lower temperature will be the dopant concentration dominate, right? So let's try to deal with these 2 regions. Is a high temperature is intrinsic, which is a Schottky defect dominate. So based on the knowledge, you know the Schottky defect. So the Schottky defect is going to help is going to produce the pairs of vacancy VFE and VO, and try to write down the rate constant at equilibrium conditions for this equation. Then you can write down is a vacancy fraction at iron side, vacancy fraction at oxide side. You can get the Schottky defect formation energy divided by KT. And because the numbers of VFE will be the same with VO, then you can get the vacancy fraction is expressed like exponential minus Schottky defect formation energy divided by 2 kT. So now we know the vacancy at iron side, so just substitute this into, so we can easily get the diffusivity can be expressed like this, and dV is here migration energy and times F. And for the dopant, as we mentioned, okay, so if you take a log on log D and over 1 over T, then you can get the slope is included 2 terms, is Schottky defect formation energy and migration energy, enthalpy, sorry, because you need to separate this gives free energy into H minus Ts, okay? So at low temperature regime, as you know, we doped the TiO2 into this iron oxide. So the Ti with 4 positive charge is going to sit on the vacancy at iron with 2 negative charges. So 4 minus 2, we will get 2 positive charge here, and O will be sit on O. And as you know, you have 2 O, right? So you are got a vacancy at iron side with 2 negative charge. So in order, the purpose here is we need to know the concentration or vacancy fraction at iron side. Here, 1 mole, you got the 1 mole of TiO2, and TiO2 is, you know, how much dopant TiO2 you are going to dope in this material. So the self-diffusivity for iron is can be expressed like the dopant concentration times the dV times F. So when you take a log on this term and versus the 1 over T, only got this, this is constant, right? Because you know how much titanium oxide you dope in this material. So you got the migration enthalpy term here. Okay, so the same idea, as long as you fit it here, so as long you can, based on this fit, you got the HVM migration energy, then you know the slope here, so I can get a Schottky defect formation energy for these materials. And however, in this case, we also observe a region can be fitted to the third straight line. We call it a non-stoichiometry effect. This effect is due to the material we are talking about is iron oxide with a 2 positive charge. If we put this iron oxide in the oxygen, then this iron with 2 positive charge is going to lose the 2 electrons, and the oxygen is going to receive these 2 electrons to become the oxygen ions. So you sum this equation up, you got the Fe with 2 positive charge react with oxygen will become Fe with 3 positive charge and the oxygen ions. So this equation tells you what? In this ionic material, some irons is with 2 positive charge, but in the presence of the oxygen, some irons will become with 3 positive charge. So some iron ions are 2 positive charge and some are 3 positive charge. In this kind of cases, we call this effect is a non-stoichiometry effect. Okay, so in order to simplify this equation, we express like this. So iron ions locate at iron ions before the non-stoichiometry happens. But when this iron react with oxygen, then that will come out the iron ions with 3 positive charge is going to occupy at the vacancy at iron ion with 2 negative charge. So that will become 3 minus 2, so it will become 1 positive. And oxygen here, and that will left a vacancy at the iron side with 2 negative charge. So you can check a look on these figures. When this ionic material receive oxygen, then the iron ion is going to move to here, and this iron with 2 positive charge is going to becomes with 3 positive charge, because it's going to it's going to lose. It was with 2 positive charge, right? And it's going to lose the electrons, so it will become 3 positive charge. Okay, and this iron ions with 2 positive charge are going to satisfy to reach the local charge neutrality. So that will become like this. So this is an important equation. In order to simplify this, I drop this term out. So in the beginning, we have oxygen gas oxygen at oxygen side with neutron vacancy will have, and the holes with 1 positive charge you can consider as a hole at the iron side. So in order to write down this rate constant at the equilibrium condition, we can write down V is the vacancy fraction times the holes fraction square, because 2 is square, divided by, this is gas, so it will be the partial pressure of oxygen, and the order will be 1.5. And this equation, the formation energy for this non-stoichiometry effect, we call it a delta G. And based on this equation, we also know if we have 1 mole of vacancy, we got 2 mole of hole. So 1 mole of vacancy, we got 2 mole of hole. So we got the release relationship. So we directly substitute this with this one. So finally, we'll got the vacancy at iron side can be expressed like this. So this vacancy is going to change or proportional with partial pressure of oxygen, and also the exponential minus energy term, and also the temperature term. So as long as we know this, we can substitute this one, right? So we can get the self-diffusivity for this ion in the non-stoichiometry region. So based on this, you take a log on this term. So if you log this one within the temperature, because you versus the 1/T, so this region actually is what? is enthalpy, and will be enthalpy minus enthalpy divided by 3. And also dVF, this is a migration energy term. Okay, so as you know, this black curve actually is a sum of these 3 effects. And by the way, as long as you got this experimental observation, and after fitting with these 3 curves, and based on the dopant one, you can get the HV migration energy for vacancy. And as long as you know the slope, you know this one, then you can get this chemical reaction, the enthalpy for this chemical reaction, for this non-stoichiometry effect. And also you know the slope for intrinsic, right? And you also know the vacancy migration and enthalpy, so you can know the Schottky defect formation energy in this your interesting materials. Okay, so let's give you more example. For example, like if you try to increase the concentration of the dopant, the diffusivity, this red line, straight line, is going to increase, right? It will become here, here, or here with increasing dopant concentration. And also, if you increase the partial pressure of the oxygen, then this curve is going to increase proportionally. And also, if you decrease the partial pressure of oxygen, this is going to decrease until somehow probably you will become just this curve can be only fitted with 2 effects. So this result implying that this material is sensitive to oxygen pressure, the pressure of the oxygen, so can be a oxygen sensor. And you also can know the suitable working temperature, because for this case, for example, like this case, this temperature region, you can observe a non-stoichiometry effect, and within this region, at different temperature, the diffusivity for ion will be different, right? And within this region, if you try to decrease the partial pressure, then the diffusivity will change in the meantime. So this is how this material can be used for the oxygen sensor. Not only can really sense the oxygen pressure, the value for oxygen pressure, and also can be slightly calculate or roughly measure the temperature effect, right? Because based on this, you know when you change the temperature, the diffusivity change in the meantime. So it can be a temperature sensor somehow. As long as you, right? So my opinion is, if you think this is a dope material, I mean, since this is your material with dopant, then first of all, probably you can do is you measure the log D for your interesting ions at different time point and get this black curve. And depending on how this curve looks like, you do the fitting stuff. If the curve is straight line, then only one parameter dominate the diffusivity. If the curve is look like the curve one, like this, then that implying that during this temperature regime, actually there are 2 mechanisms involved in this diffusivity. And for specific temperature regime is for this region is intrinsic dominant, and this region is dopant dominant. But if the data you observe is like this, can be fitted with 3 straight lines, that means in your interesting working temperature, there are 3 different mechanisms control the diffusivity of iron ions. Okay. And as long as you fit in, you can get the energy term. As long as you fitted your data, then you know this value, then you can get this one, and also can know the fact defect formation energy of your materials. Okay, so I'm going to give you a brief summary of diffusion mechanism. We can, based on the quantum mechanics idea, then we got the diffusive, and also based on the radial probability method, we can get the diffusivity can be expressed like the total atomic jump rate times the mean square jump distance divided by 6 times the correlation factor F. F is related crystal structure. And for the interstitials and vacancies, then F equals to 1. And don't forget, what's a vacancy-mediated self-diffusion? It means the diffusing atoms, there's must a vacancy nearby the diffusing atoms. So that will allow diffusing atoms diffuse. So the diffusivity can be expressed like a XV, vacancy fraction, dV, vacancy migration energy times F. For the interstitial C, self-diffusion is the same idea, right? There must be a self-interstitial defect nearby the diffusing atoms. So that will allow the diffusing atoms to diffuse, and the self-diffusivity will be equals to Xi, vacant interstitial atomic fraction of interstitials, diffusivity for these interstitials, and times F. And we also show you how to determine or obtain the vacancy formation energy and the migration energy by what? By, first of all, we need to determine the enthalpy, total enthalpy. Then by using the by measuring the thermal expansion minus the contribution from the lattice constant, the increase from the lattice constant, then you can get the vacancy formation energy. Then use the total energy minus enthalpy minus the vacancy formation enthalpy, then you can get the migration energy term. And also, we also provided you some possible is the material is a dope material. You dope some solute atom at substitutional site and want to know the self-diffusivity for this solute atom through the vacancy-mediated diffusion. Because you dope the other types or kinds of solute atom at substitutional site, so that will cause the bond strength difference. As long as a bond strength difference, reduce mass difference, so the gamma prime atomic jump rate will be different. So there are 3 different types of atomic jump rate involved in this kind of vacancy-mediated solute diffusion. So we need to consider the rate determining jumping process is what. Then we can formulate the self-diffusivity for this solute atom. And next, the end of this lectures will be, we give you some examples about the diffusion in ionic solids. But this ionic solid actually is through vacancy-mediated diffusion mechanism. And we have 2 different kinds of defects. The first one is Ch4 defect. The second one is Frankel defect. As long as the most important thing is you need to determine the defect concentration. In the Ch4 defect is the formation of pairs of vacancy, anion and cation vacancy. So the self-diffusivity is easy as long as you know the vacancy fraction, then times the dV, times F, you can know the self-diffusivity for specific ions. But if it's a Frankel defect included 1 vacancy and 1 interstitials. Right? When you want to describe the self-diffusivity for interstitials, then you use XIDIF. But if you want to explain the self-diffusivity for the other vacancy one, then you need to use the this idea. This for describe the other vacancy. The other ions diffuse through the exchange with the vacancy one, right? Okay, so today we ended the